Alright, well, hello everyone. Thanks for coming. My name is Ilya Verzhbinsky. I'm a senior at Lowell High School, and this summer I worked at the Lab of Cardiac Biomechanics at the VA, co-PI'd by Dr. Mark Radcliffe and Mr. Julius Guccione. So the primary purpose of their lab is to create finite element computational models of the heart to investigate the effects that different surgical procedures and different cardiac devices has on the heart. So I'll start by giving you guys a brief overview of heart failure. So heart failure, roughly 56,000 Americans die from heart failure each year. And most heart failure cases arise from what is called a myocardial infarction. And what I dealt with this summer was a myocardial infarction in the left ventricle, which is the lower left chamber in the heart that pumps oxygenated blood to the rest of the body. Now after and a myocardial infarction is when a portion of the cardiac tissue dies from a lack of oxygen. And after a myocardial infarction occurs in the cardiac wall, the left ventricle undergoes a remodeling process that is characterized by a swelling of the cavity, as you can see here, and a thinning of the cardiac wall around the infarct zone. And this increase in left ventricular volume is largely related to mortality. So as a result, many devices have been made to counteract the effects of left ventricular remodeling. The device that I studied this summer was the cardiokinetics parachute. It is a parachute-shaped device. It's catheter-based also, and it is percutaneously delivered through the femoral artery into the left ventricle, where it opens up and partitions the left ventricle into upper and lower portions. Now, it has already been shown to decrease left ventricular volume after a myocardial infarction. However, the mechanisms behind this decrease in volume is unknown. So that's what I did this summer. So in order to go about figuring out how exactly the parachute works, we created finite element computational models based off a patient's pre-op and 6-month post-op computed tomography data. And this data was received from a patient who had undergone the parachute procedure. We were left with 3 models. The first model we created was a pre-op model based off the pre-op CT data, and we used that as a reference point to calculate stress and to see what the stress was in a heart that had, without the parachute, that had experienced a myocardial infarction. Second, we simulated the parachute implantation process to determine the acute effects of the parachute on the cardiac wall. And finally, we created a 6-month post-op model based off the 6-month post-op CT data that we received from the patient, and this was used to determine the chronic effects of the device on the cardiac wall. In the next slide, I'm going to show you guys a quick animation of how we simulated the virtual parachute procedure. So the parachute was collapsed and then reopened, and then the cardiac cycle was simulated. So these are our results on myofiber stress. So I'd like to be very clear what we mean by myofiber stress. Stress is the force on a given area in regional zones of the myocardium, and it was calculated, and in our diagram here, red denotes the higher regions of stress, whereas blue denotes lower regions of stress. So you can see we also measured stress at end systole or end contraction and end diastole or end filling in all 3 of our models. So as you can see, the end systolic stress is largely unchanged, whereas the end diastolic stress is very much reduced as a result of the parachute implantation. We also measured stroke volume, which is the amount of blood leaving the left ventricle, but that was largely unchanged in all 3 models. So the conclusions were the primary mechanisms behind the parachute device are a decrease in myofiber stress at the end of end diastole, and stroke volume and stress at end systole were largely unchanged. So the future implications or the future directions of this project are, since the company that makes the parachute creates multiple sizes of parachutes, we would like to perfect our finite element models and make them more efficient so that we can retrieve patient CT data and figure out the optimal size of parachute and relay that information to the surgeon before the procedure is done. So I'd like to acknowledge my 2 PIs, Mr. Julius Guccione and Dr. Mark Radcliffe, Ms. Zihong Zhang and Mr. Liang Ji for their mentorship, Will Morrill and Joe Pantoja, they're med students that helped me out a lot, and of course Mr. Shapiro and Julia Yi and all of the rest of Lowell MSTP for giving me this amazing opportunity to work this summer in the UCSF lab. Thank you.